So this is the last video in this series, which will treat the cosmos, our universe. Its universe is a very complex machinery. It is somewhat surprising in many aspects, as you will see, and it's very dynamic. There are variations of some parameter which we believe is constant, but in fact it varies with universe expansion. And the whole machinery, it's quite complex to get your head around. It's not very difficult, but the ideas comes out which are strange at the beginning. At least you have to get used to them, and we will look into this. So you have physical laws, of course. You have constants which are varying within these laws, and you have phenomena which is connected with the geometry of the universe, etc. Okay, so to start we will have a look at what is the real physical constants, which are invariant of the expansion of the universe. You have the certain number, and so we will have a look at this. First of all, you have the Daon mass. That is, the mass of the Daon is always constant, it doesn't vary. This definition of the Daon mass is not so easy to do, because it's really the object which is absolutely fundamental. So to define a mass of this, it's complicated. You just follow the definition of mass we usually do, and we put this inside with the Daons, and we obtain a mass. So this is difficult to define, but the value is quite precise. Okay, then we have the charge. The charge is also a constant, in the sense that the charge is simply a radial equilibrium. It could be positive or negative. This radial equilibrium comes from the fact that the Daon are radially pointing outwards or inwards on a sphere, and this is the electron and the positron. So this is the unit charge, and when you come a bit away from the charge, and you have a specific value of interaction which is defined as a radial equilibrium, constant value, and this you can put to 1 and minus 1 positron and electron, and then if you get some variation, it depends on the column constant before this charge, which is containing the variations of the charge value in reality. So the charge is just plus minus an integral value. Another constant is number of Daons within the universe. That is constant also, as we have discussed earlier. Then we have the fine structure constant. Fine structure constant is the transverse velocity of the associated wave divided by the parallel mean velocity in square, as you can see here. So this is a constant. So this is an important parameter, or an important constant in the electronic inside an atom. Okay. Then we have the light speed. Light speed is always also a constant, and in fact velocity in general are constant. They are always the same value, independent of the expansion of the universe. We have also that the internal action within a particle, whichever, it's also a constant, but this constant is different for each particle. Each different type of particles has a specific constant associated with it, which is constant in the expansion of the universe. This is okay. So this is the internal constant. So this is all. Then the next series of constants, which in fact are parameters coupled to the expansion of our universe. We will then make a list also of this. We define first a parameter which are defined as a ratio between the free Daon size divided by the free Daon size in this given moment. We call this a P. This is proportional to the radius of the universe divided by the radius of the universe in this moment. But this is not exact because you have free Daons going into the mass which are increasing, which means that you have some small correction term for the universe radius. You'll better think of this as a ratio between the free Daons. I mean, this is also not so good because you can have variation of the size of the free Daons with the radius of the universe. We will come into this later on. So both of these type of thing are to take with some caution. In principle, they are good. It's okay, but you have small variation. We have to be a bit careful. Okay, so now we take first the mass. Mass of any particle is proportional to the free Daons and therefore also to the size of the universe. So the expansion gives that the mass is increasing. So you multiply the mass you have now with p, which we have just defined, and you obtain an increase of the mass. Then you have the radius of a free Daon. As we say, the number of free Daons within the universe is constant. So when the universe is expanding, also the free Daons are expanding in the same way. Then you have the electron's reference radius, Re infinite. Now this is increasing with the universe with a power p to a power of 4/3. That means that the reference radius of the electron is growing faster than the universe itself. This is very important to come up with later on. Okay, with this we can then define the Coulomb constant, where we have inside the Coulomb constant we have some constants or parameters which we have already seen, just seen what happened to them, and we obtain that the Coulomb constant is proportional to p again, but now to the power of 7 to 3. So this is a very strong variation of the Coulomb constant with the expansion of the universe. The Planck constant, which is a variant of a Coulomb constant, follows the same thing. That is p to the power of 7 divided by 3. You just divide by v velocity, which is a constant. So you get the same relation. Then you have the wavelengths of the associated wave of an electron, for instance. And this is growing with p when you have an expansion of the universe. You have that this wavelength is increased by the p to a power of 4/3. And that is why that's okay. So this is why you have the size of the atoms, molecules, and all matter in general will also increase with the same value. Since the wavelength, which is an important part of the electronic configuration of an atom, this is growing with p to power 4/3. So all matter will grow with the same factor, p to 4/3. So matter in general is increasing with the expansion of the universe. So we have the Hubble parameter is somewhat more complex. You have the relation between the speed of expansion now and the future. You have so this is not exactly the p. This would be divided by p. So the Hubble constant is reduced with p, increasing the expansion of the universe increases its radius, and this is reducing the Hubble constant. And the speed of expansion of the universe, it's at the moment, in fact, this is more or less constant, let's say. But if you have a variation of this velocity, then the Hubble constant will follow the speed. And then we take finally look at the gravitational constant. And the gravitational constant, as you can see here, is proportional to the p to the power of 2/3. So the gravitation is growing with the expansion of the universe. So now we have a look at time. What is time? Time is an interesting parameter. I would suggest that in the interaction between atoms, we have that everything is coupled to the electron's behavior within an atom. So if this atom are changing, then also the time will change. And in fact, if you look to this, you see that the wavelength of the associated wave is growing with expansion of the universe to p to a power of 4/3. And if you put this in the level of the atom, since the size is bigger, also the time will slow down. And it's the same thing, it will be proportional to the p to the power of 4/3, also the time. The time is slowing down with the expansion of the universe. And now, since the size of the atom is growing with the same thing, you have the size of the atom divided by the speed, by the time, and this gives that the velocity of the electrons are constant. So that means that the velocity in general, that is a constant, it doesn't vary. You have also the rotational speed of the Daons, which is proportional to the speed of light. So this doesn't vary, it's always the same. The variation is in the time and the size, not in the velocity. So we have a look again at the force of gravitation. If we include now the variation that we have seen in the masses, we obtain this type of equation here, and this goes with the gravitational force is increasing with the expansion of the universe, with a factor of p times to the power of 5 divided by 3, which means that all gravitational forces will grow with this value. And this leads to a radius of, for instance, Earth around the Sun, let's say, which are growing with the p to the 5 divided by 3. So this is an increase of the size of the solar system, of the galaxies. Everything will grow, which has a gravitational influence, and it grows much faster than the universe itself. So this is somewhat strange. We have also the influence from dark matter will grow in the same way. So this is interesting to reflect, to think about. So this is, if you imagine now that with the expansion, that is also with the time, is going with the expansion of the universe, we are growing faster than the universe itself, which means that relative to ourselves, the universe will become smaller and slowing down. And also the time will go slower and slower than the universe expansion. So this leads to several complications. For instance, that you have that if you imagine the Earth and you displace it in time backwards, let's say 10 billion years, something like that, then we will have reduced our size much smaller than the universe has reduced, which means that relative to us, the universe has become much bigger. And also the distance between galaxies has become bigger. And while the galaxies have become smaller, the relative distance between galaxies is now bigger. And also, since the time has become faster, everything happens with more speed. So the development, for instance, of galaxies and things has speed up and becomes much faster when the universe was smaller. And that is exactly what you see today in the latest development of telescopes. Okay, and let us go to redshift. What happens to the redshift? So the redshift is the fact that when you see a photon coming from far away, back in time, let's say, then you have that associated wavelengths has become longer, and you are moving towards the red side of the spectrum. And the question is why. Now, if we examine this in a bit more detail, we see that the photon is emitted from some atom very far away and back in time. At that time you had that mass was smaller, and if you look to an atom, the photon coming out from an atom would be with a lower energy. And if you now put this into the equations of energy, you find that this energy is lower compared to the size of the universe. We know that the mass is constant. No, mass is growing with the universe expansion. So earlier the masses was smaller. So we obtain the energy of the photon at the moment of emission, and then we put in the equations that you have already seen, the variations of various things. The energy should be constant from a photon emitted in a given moment. The photon doesn't interact with anything, and so the energy of the photon should be constant. But you have a modification of the associated wave. The free Daons are getting bigger, so you have variations that you can take from the equations we showed earlier. And the result is that you have a declination in wavelengths. The wavelengths becomes longer because the photon energy at the moment of emission was lower, and this corresponds exactly to the redshift. So that means that the redshift is a direct indication of distance, or to be more exact, the relation between the free Daons at the time and free Daons of us here at the moment of emission of the photon. So this is gives a relationship which can be connected to the distance and the time. Okay, if we look now, we now start with cosmic microwave background. Now, cosmic microwave background is photons with a very low energy, which there are many around all over the universe which are coming towards us, and you want to know from where are these photons coming. And I think one possibility, there are other possibilities, but from my point of view, I think this comes from the time when the atoms were really very small. And if you take a look at this, you see that the energy of the energy levels within an atom, it was completely different. You can go to a very small universe, and in this case the energy levels was just some energy level possible. Many energies was not possible because you could not have a photon, or the energy difference between levels is not sufficient to create a photon. So you have no photon emission. But when you start to get some energy level, and you have a very simple ionization process, it's not just enough to come close to another atom and you get immediately ionization, and then the capture is, since you have many photons around, you will have capture. It's about the same thing. But this is the cosmic radiation could very well be from this stage of the universe development. Ionization is very easy, so we have many photons coming out, and then not all of them were captured, so you have this radiation background. If this is correct, then you should have the black body radiation from certain energy levels of the hydrogen, helium, etc. And I am not sure that if you can separate these different energy levels within the background radiation, because they will be about the same value, but they should be slightly different in different times. So maybe you can see some characteristic within the background radiation. I'm not sure about that, but it was a try to look after this. Okay, now let us take a bit of a look at what happens to the universe in a long range. If we look to the values of you have the values of the expansion of the universe, the dark energy, which we discussed earlier, that is proportional to 1 over radius. So the bigger the radius of the universe, the weaker the dark energy, or weaker this expansion force of the universe becomes. And if you look to the gravity, which should keep the universe together somehow, this is growing with the expansion of the universe. It becomes bigger, stronger, which means that a certain expansion of the universe you will have that the gravity becomes stronger than the dark energy phenomena. So the universe will start to slow down and eventually come to a halt. Now, when it comes to a halt, then you have some interesting thing, that is that the gravitation will go down to zero locally, because the speed of expansion goes down, the Hubble constant goes down to zero. And so when the gravity goes to zero, you will have all the stars, all lumps of matter will start to evaporate away, and you will have that the universe, the entire universe, will become some sort of plasma. So this of course will kill all life possible in the universe. And then since the gravity now become stronger than the dark energy phenomenon, you will have a contraction of the universe and going back. And this is quite complicated to calculate because of the delayed interaction. You really have to make a simulation program to have a closer look. But in principle, you have that the universe stops and come back, and then probably comes out again, and you have that the universe is like spring. It's just going out and in radially, like this. Because when you go up to the minimum size of the universe, you have the opposite effect, that the gravitation becomes weaker and weaker, and the dark energy phenomena becomes stronger and stronger since the universe becomes smaller, and you have the equation 1 over r for the expansion of the universe, and this will become stronger than the gravity, and you stop to break down, and you come to a minimum size of the universe, and then it will again start to expand. So to study this, we made in any case a simple one-dimensional program. We didn't take into account the enormous distances, which make some delayed constants, which not delayed effect. So this program is valid maybe for small diameters, smaller size of the universe, and for bigger distance you have to include the delayed interaction, which probably will give something else. So we have some starting points. The Hubble constant of today would give a starting point, and we have this minimum size of the universe cannot be smaller than a certain value, because if you become even smaller, then the electrons will disappear. There are not sufficient number of Daons, so it has to be within a very limiting thing. You cannot limit in size. You must have a size not too small, but also not too big, because you should have this background radiation, which means that you have to have a certain radius where you can have the easy ionization of atoms, and this gives another radius, so you have to be between this radius and the minimum radius. So you have some quite stringent limits of the minimum size of the universe, and then you can start expanding it using just the dark energy phenomena and the gravitation, and you can put them in equilibrium, let us say, also play around with that. So we find that minimum size at some radius of around 180 million light years, 180 million light years should be about the minimum size of the universe. And the expansion rate at the minimum size, when you have some acceleration, it should be around some 10 to minus 6 meter per second square. You should also understand that if you look to the gravitational constant, that when the Hubble constant goes in the opposite direction, that is, it becomes negative, then also the gravity becomes negative. So during the whole phase of contraction of the universe, you will have a negative gravity. That is, it's impossible to create any stars, any planet or whatever, just a plasma beating down on itself and reducing everything to the simplest components. So there's no life possible. You have the contraction is just like breathing. You have expire, use air, you increase, and the expansion you take in fresh air. So you have this expansion is full of life, the contraction is full of death. You have also that according to this program, which is not very good, but in any case, you get that we have already passed over to the phase of slowing down, and the expansion is now slowing down, and the breakthrough was 12.3 billion years from the minimum size to the period when you shift from expansion to slowing down, not increased acceleration and deceleration. Well, okay. Total now, our time we have spent about 14 billion years. You add some time because of the slowing down when you come to the minimum size of the universe. It's expanding then quite rapidly, but it takes some time. So we have some billion years longer than usually used. You have also that the radius of the universe today is around 400 billion light years. And you have that the expansion at the border of the universe today is 22.4 times light speed. So it's very, very fast. You see, this is no problem. I mean, you have the light speed is a limit, local limit of the speed between the three Daons and some other object. When you have this enormous expansion at enormous distances, then the relative velocity can be it's always c, but when you compare the center of the universe with the border, then the difference is 22 times the velocity of light. For the oscillation of the universe, we can calculate about the time putting the gravitation equal to the expansion. Then you obtain that it's around 50 billion years of complete oscillation. And of course it will repeat itself in principle in eternity. As you know, the universe has always existed. We can make another point is that the universe has a specific border, and if you try to penetrate this border, which you can, if you're close to the border, you can try to shoot a photon or a neutrino or whatever against the surface, and you hope that it will go through it. But in fact, what happens is that whatever you put through it, it's always constructed by Daons. So when it comes through the border, it cannot go through the border. It will be some extrusion from the universe border, which will extend with whatever comes through, and then you will have a weaker interaction around certain extrusion, and the Daons will grow. And when they grow, they become weaker, and they will be attracted by the smaller Daons within the universe. So this extrusion will stop, and then we'll go back to the universe. So the border of the cosmos acts like a perfect mirror. Nothing can escape from our universe. Okay. We should during the universe expansion, you have this creation of black holes in almost every galaxy, and they are accumulating mass all the time, become bigger and bigger. They contain more and more mass, and then what happens is that when the universe first expansion reaches maximum value, then you have the maximum mass inside these black holes, and then the gravitation goes down and becomes even negative. So what happens is that this black holes becomes white holes, that this is now giving away their mass in radiation and whatever to the surrounding. So the black holes become white holes, expelling all their mass, and you have spheres around these black holes, which is going away like this. Even after you have consumed all the mass of the black hole, then this sphere of matter still expands, and it continues to expand until it's encounter other spheres of other black holes, which is expanding in the same way. So the result of all this will be that you will get a big zero, which contains zero mass, big spheres. So what is what you say is called super voids. So enormous black holes, and then you have at the border of encounter with other expanding spheres, you have a very intricate distribution of mass around these voids, depending on the geometry of the position of the black holes. So there you get different enormous voids, super voids of different forms and size. Okay, so this is the explanation for the super voids, which you find in space quite everywhere. Now, if you look with a telescope on a distant galaxy, what can you see? You can see you have a certain size of the galaxy in your telescope. So the size of a galaxy, when you look through the telescope, it comes from first of all, when you're looking very far away, you have that the size of the galaxy is reduced by the factor p, parameter p, to the power of 5 divided by 3. Then the photons emitted from this galaxy will arrive towards your telescope, and during this time you have expansion of the universe, which will lead to the photon is moving away from each other, and when they arrive you will have an image of a galaxy which is reduced by p to the 2/3 instead of 5/3. So this is even much smaller than you see in the telescope. You have also, of course, that the time is reduced also, so everything goes quicker in this smaller galaxy. The time is accelerated by p, parameter p to power 4/3, which means that you have all activity within this galaxy is accelerated. So the development is much faster. You have more emission of photons because the recreation of stars will go faster, etc., etc. And so this is the explanation for the development of galaxy and the activity that you see in modern telescopes now. So, okay. If we go to the move away a bit from the Earth, then you are getting into problem with a local reference frame. I mean, how do you decide which is a good reference frame? If you're far away from heavy masses, then you have to make some summation of all the surrounding masses to obtain the free down flux around you. And so this is quite easily done. As you see here, it's just to sum up. You have to know the distance from the big masses, and you can then calculate the speed of the free down flux surrounding you, which then you can use as a reference point for any, if you want to make some experiment, for instance, inside your spaceship or something like this. But then you have to be careful about the spaceship itself and its influence, of course, so this is, be a bit careful. Okay, then we have a problem with stellar aberration. This is a problem which almost killed the ether theory of frame dragging ether, because when you have a telescope pointing to a star far away and you follow it in time, you find that this star changes the angle relative to the telescope, which means that this photon is going straight towards the telescope, while the Earth is moving around in an orbit around the Sun. So they say, since this is the case, you could not have a bubble, let's say, around the Earth, because then this should influence the direction of the photon. And the problem here was essentially that they did not understand well how the photon is its characteristic of the photon. We have already examined the photon in an earlier video, so we'll see the DAON theory around this is the following: that the photon pushes himself towards the limit of velocity. It accelerates. So when you pass from one bubble to another, if we start with a longitudinal sense of the direction of the photon's speed, you have that if you have a bubble coming against you, for instance, then the relative speed between the photon and the free Daons becomes above the light speed. In this case, the photon will slow down to stay on the velocity of the light speed. The same thing if you get a slowdown due to the difference between the speed of the bubbles, then the photon will accelerate to the speed of light without changing its mass or energy. Now, if we now see to the transverse sense, if you have some free Daon flux coming transverse to the direction of the photon trajectory, then the photon, it doesn't like to have a transverse flux. He will turn until he gets the total flux should be exactly parallel with his velocity. And if you do that, you have a change of direction, so that you have the speed of the photon going directly against the flux. Then it's like you eliminate the transverse flux in somehow, so that from a third observer far away, he will see the photon going absolutely straight through all bubbles or strong mediums form big bodies. The photon just goes straight through, always perfectly correct because of this characteristic of the photon. The only thing that can bend the trajectory of the photon is gravitational fields when you come close to a big mass. And so from the Earth's point of view, it seems like the photon goes straight and doesn't care about the trajectory of the Earth. In fact, this is absolutely correct. So this doesn't make any specific reason to abandon later theory. Okay, then we have the Pound-Repke experiment, which was in fact two installation where you have a distance of 22 meters between an emitter and a receiver, and it's some sort of photon atomic traps which are extremely sensitive. They are the same atoms, so they have exactly the same levels of energy, and you have a very precise measurement of the frequency difference between these two setups. So they used some frequency shift calculation using general theory of relativity and some gravitational considerations. So they measured very precisely the frequency difference between the emitted frequency and the received frequency. They made some oscillation in the radial sense of the emitter to see when he captured the emitted photon, and you can extract the difference in frequency connected to the velocity of the receiver. If we translate this into DAON theory, what happens is the following: is that when we looked at gravitation, we saw that the Daons are compressed so that you have smaller Daons on closer to the mass, and when you move up, then the Daons becomes bigger, and so you have a difference of size of the Daons surrounding the atoms, leading to a photon emission which is slightly off in frequency from the emitter and the receiver. And if you calculate this within the Daon theory, you get a difference of frequency, which is exactly what they found experimentally. So it's perfect agreement with Daon theory. Then we made another, we examined also the time in GPS satellites. In GPS satellites, you measure the atomic clock, essentially. So we have a clock on Earth and a clock up on the satellites. And you send signals and you compare the different difference in time. And then you make some triangulation, trilateration of geometry on Earth compared with the satellites. And you find the precise position. So this is essentially is due to the difference in time. And this they tried again with general theory of relativity, special theory of relativity, since it's moving also in the azimuthal sense. And they obtained some results which agrees quite well with the experimental results. For the Daon theory, we made exactly the same thing. We calculated now the difference in size of the three Daons from up to the satellite and down on the Earth's surface. And we also corrected for the Planck's constant, which is included in these calculations. And we find the difference in frequency in perfectly agreement with the GPS data. So this is again a demonstration that Daon theory works perfectly nice with all these different experiments. We should say something about the SC units, standard international units. These are, most of them are varying with the expansion of the universe. And in principle, that we now can measure certain parameters or constants down to the 10th digits, then you should be able to see the variation of these constants in time. It will take a couple of years distance. But since these SA units are varying, several of them in a certain manner, you have difficulties to really measure the absolute values of this constant, because in reality it becomes subjective measurements. So since the changes are very slow, you can say, well, okay, it's not very important. But in principle, this SE unit has to be revisited to remake completely different approach to this to have something correct. But then in any case, you will have SE units which are varying with the expansion of the universe, so you have a small variation. So it's a problem to be looked at. Okay, then we have different types of energy, what we can define. So first we have some energy associated with mass, which is the number of Daons included in some body. So you can see in the decay, for instance, from a particle, you have the decay, so the number of Daons is constant, and they just found in the decaying product. And this is one type of energy. You have energy which is connected to the number of Daons, like the gravitational potential or decay or other products like kinetic energy, collisions, etc., etc. Then you have another type of energy which is connected to movements. That is, for instance, Daons rotating in an electron or in a photon. These are also an energy, but it doesn't involve the number of Daons, but it's just a rotating movement, so it's a momentum, let's say. And you can have a vibration, displacement, or I don't know, any kind of energy where you don't have a transmission of number of Daons. Then, so this is another type of energy. So it means that energy is not always connected with mass through c², but you have also energy which is there in the rotation, for instance, but not a displacement of mass. So, okay. So to finish this, we should have a look at the universe as such. So we have that the proton cannot be created. is always a very extremely stable particle. So if we succeed somehow to destroy a proton, then this means that the universe will eventually disappear, because you cannot have some destruction of essential parts of the universe again and again on the long infinite range of oscillation of the universe. The universe tends to disappear, which means that the proton must be extremely solid, otherwise it would be a serious problem. And so you have a proton cannot be destroyed inside a black hole, for instance. You cannot crush a proton, it's not possible. So this is a limit of density of a black hole, because otherwise we should not have a universe. So this means that you have the black holes are protons and electrons, neutrons, extremely dense. Okay, so you have also something else, and that is that the situation of positive protons and negative electrons is permanent, cannot shift. So our universe has this kind of asymmetry, which means, since nature likes symmetries, it's most very likely that there is another universe where the situation is contrary, that is electrons is positive, and protons is negative. And in this case you have two spherical universes which should move away one from the other to avoid any further problem. Of course, if you have such a pair of universe, then there is nothing to say that there are not other pairs of universes. So you could have an infinite number of universes within an infinite space of void, going away from each other. Of course, they had to have big distance between very big distance from each other, so that you don't risk collisions and other things. But nothing is impossible within an infinite void. So, okay, I think we have stopped there. We cannot go much further. Of course, we don't answer metaphysical questions like who made the universe, why, etc. This is questions which has no answer for the moment. I don't see. I don't want to answer this question in any case. Okay, so this is the end of the presentation of the Daon theory. Of course, I should show you the book. So this contains Daon theory. If you take Google and you say the Daon theory book, and you will have indication where you can obtain this book. Okay, so have a nice life. Bye bye.